Alright, before we start looking at higher gain amplifiers, I wanted to look at what happens with offset in an operational amplifier. And we're going to look at a differential pair with a resistive load first. So let's go back to our traditional differential pair with resistive load. And the traditional assumption that we've made is that all of the circuits in each of the paths are well matched. In other words, the resistance in the drain of the transistor is equal to the other resistance. So we're saying RD1 is equal to RD2. In this case, what we're going to say is that RD1 is not equal to RD2. What happens then? And further, we're going to say that M1 is not equal to M2. What happens to our differential output voltage? And we'll use an ideal current source here. Okay, so we know that for a common mode input voltage, we should see nothing if the common mode voltage, for a common mode input, we should see no output voltage develop. But if our circuits don't match, then we will see some output. And the way that we analyze this circuit is we can assume that we do have a perfectly well-matched circuit. In other words, RD1 does equal RD2. We can say that M1 does equal M2. And what we're going to do to compensate is we're going to place a voltage source, VOS, V offset, in series with the input of one of the inputs to our differential pair. So this is our actual circuit with mismatch. And this is an ideal source-coupled pair with an external voltage offset. So what we're saying is that any internal offset in our circuit here can be modeled as an external voltage offset. Which we've added here. Now, our offset voltage, VOS, is going to be due to a couple of things. So, you'll see this more when we make a discrete operational amplifier later in the semester, but primarily it's due to mismatch between M1 and M2. Now, M1 and M2 can be mismatched for a couple of reasons. One, W over L might not be equal, and the VTHs of each of the devices might not be equal. And this is due to process voltage and temperature variation. Which we will abbreviate PVT. And if we were using resistors instead of transistors as the load, RD1 and RD2 might not be equal. And this could be due to geometric variations. When we fabricate these resistors, they might have different sizes. And it can also be due to thermal mismatch between the resistors. If we're making an integrated circuit, a lot of resistors have different temperature coefficients, and they might vary slightly between the two resistors, causing that mismatch. Okay, so we're going to set up the analysis for this circuit. So the definition of our offset voltage, VOS, is equal to the VID value needed for our output differential voltage, VOD, to equal 0. So ideally, V offset would be equal to 0 because we'd like 0 volts out when 0 volts is put in. But due to that mismatch, it's not going to happen. So here, we have the input of our circuit, and we're just looking at small signal analysis. So this would be connected to a high impedance current source, so we're going to leave that out. We're going to put our offset voltage into the loop. We have M1 and M2. And we know we have a VGS1 here. And we have a VGS2 here. So if we do KVL around this loop, KVL around the loop says that our offset voltage minus VGS1 plus VGS2 is equal to 0. Or our offset, VOS, is equal to VGS1 minus VGS2. Now ideally VGS1 and VGS2 would be equal to one another, but let's go ahead and write out our expression completely. So we can say VOS is equal to VTH1 plus a VOV, which we can write as square root of 2 times ID1 divided by Kn times W over L1 minus VGS2, which is equal to VTH2 minus square root of 2 times ID2 divided by Kn times W over L2, where remember Kn is equal to mu n C ox. All right. Now we're going to define our mismatch statistics again. So remember, whenever we look at mismatches, we talk about them in terms of an average and some kind of statistical mismatch. So we're going to define delta ID is equal to ID1 minus ID2. In other words, the difference between the two currents. And ID is the average is equal to ID1 plus ID2 divided by 2. We can write the same mismatch statistics for delta W over L is equal to W over L1 minus W over L2, and W over L is equal to the average 1/2 W over L1 plus W over L2. We can also have a mismatch in threshold voltage, so we can say that delta VTH is equal to VTH1 minus VTH2, and VTH is equal to the average VTH1 plus VTH2 divided by 2. And finally, we can look at our resistor mismatch. Delta RD, the difference between the two resistors, RD1 and RD2, and RD is equal to RD1 plus RD2 over 2, the average of the resistors. All right, and finally we'll rearrange these definitions, and we could say that ID1 was equal to ID plus delta ID over 2. ID2 is equal to ID minus delta ID over 2. W over L1 is equal to W over L plus delta W over L over 2. And W over L2 is equal to W over L minus delta W over L over 2. And our VTs, VT1 is equal to VTH, or sorry, this is VTH1 is equal to VTH plus delta VTH over 2, and VTH2 is equal to VTH minus delta VTH over 2. All right, so we're going to take a break here, and what we're going to do is substitute these mismatch parameters back into our expression for offset voltage, and we're going to solve and figure out what our offset voltage is when we're faced with these parameter mismatches.